Bonjour tout le monde, bienvenue à ce nouveau séminaire quantique Ivado. L'hiver est arrivé, mais nous, on se réchauffe avec nos séminaires. Ivado, toujours cette organisation qui cherche à intégrer les gens dans ce projet de développement de l'IA et aussi de son interface avec le quantique. On a peut-être un petit peu moins de gens aujourd'hui. Vous savez, Ivado fait partie de l'Alliance pour l'algorithmique quantique avec Sherbrooke et l'ETS. L'ETS a un événement drôlement organisé avec IBM aujourd'hui, alors qu'on a un chercheur réputé d'IBM ici. Alors, on a moins de personnes, donc le groupe de l'ETS n'est pas évidemment chez lui aujourd'hui. Mais de toute façon, quoi qu'il en soit, uh, on a un programme remarquable. So we have a really big star of quantum computing with us today, with Sergey Bravyi. He has an amazing pedigree. He did his PhD in 2003 at the mythical Landau Institute for Theoretical Physics. He's worked in the area of condensed matter physics to some extent. His supervisor is also the celebrated Alexei Kitaev, monument in the field. And then he did a postdoc at Caltech with John Preskill, another nobody in the field. And since 2006, possibly 2005, because Sergey told me that it's been already 20 years he's been at IBM. So he joined the group at IBM, where he has been since, and he's really developed a quantum group of which he's the leader. He's internationally known for his work in quantum algorithms, error correction, topological phases of matters. There are things that bear his name, like the Bravyi Kitaev transform or the Bravyi Gaussian algorithm. And so we're really, really delighted to have him with us. Thank you for coming, Sergey, and the floor is yours.
Thanks a lot for introduction, Luke, and for bringing me here. It's a great pleasure to be here. Today I will talk about something which is relatively new to me. It's about differential equations, and this is a joint work with my IBM collaborators. Robert and Mike are experts on computational fluid dynamics, and Sergey works on quantum applications. And this work is available on arXiv. And by the way, if something is unclear, don't hesitate to interrupt and ask questions. As you probably know, solving classically hard problems on a quantum computer requires a lot of gates, and we have to do very expensive error correction to protect this gate from noise. So noise is our biggest enemy in quantum technologies. But today, basically, we ask, can we make noise our friend? And we imagine that we already have a fault-tolerant quantum computer, which is effectively noise-free. But instead, we apply noise to the problem that we are trying to solve. So what exactly does it mean? Well, a formal definition may depend on the problem, but for example, noise can describe some uncertainty in input data, or maybe some parameters that are beyond our control. And we would like to find a problem which is extremely hard in the noise-free case, but which becomes easier when we add noise. But it only becomes easier for quantum algorithms, and it remains hard for conventional classical computers. And of course, we would be happy if this problem has some practical relevance. So Sudoku might not be a good example. And today I shall talk about solving nonlinear differential equations. And I will first define the noise-free problem and explain why we believe it is very hard. And then we shall see what happens in the presence of noise. Okay, so we consider a system of ordinary differential equations with n variables. T is evolution time. X of t is n-dimensional state vector. And the dynamics is governed by some drift function f that maps Rn to Rn. And our goal is to compute certain property of a state vector at time t, given initial condition at time 0. For example, we can ask what is the value of variable x1 at time t equals 100. And I will consider sparse quadratic ODEs. And this means that each component of this drift function is a quadratic polynomial in F. It has a linear part described by some sparse matrix of coefficients and a quadratic part described by some sparse tensor. And we also assume that this initial condition x at time 0 is a sparse vector. So for a reasonable definition of sparsity, this entire system has a succinct description of size only logarithmic in n, or maybe polylogarithmic. So this is example of a problem with small input, small output, but getting from the input to the output appears to require a lot of work. For example, if we use standard ODE solvers like forward Euler method, the runtime would be at least linear in n, because we have to store the entire state vector in computer memory. And basically, the main question for this talk is there a quantum algorithm that can solve sparse quadratic ODEs with the runtime only logarithmic or polylogarithmic in n and polynomial in t evolution time. So we want the runtime to scale as some constant power of log n and some constant power of t. That's the goal. But unfortunately, it is well known that some quadratic differential equations can exhibit singularities when the norm of the state vector becomes infinite. As we approach a singularity, some bad things can happen. For example, if we use classical ODE solvers like Euler method, we would have to make time step progressively smaller as we approach a singularity point. So this is something we want to avoid. And so we restrict attention to a special class of ODEs such that the norm of the state vector does not grow with time. So we say that a system is divergence-free if the drift function obeys with conditions shown here. So the first condition simply says that drift function is a divergence-free vector field. And the second condition is analogous to skew symmetry for this matrix of coefficients and tensor of coefficients that I defined before. And from these conditions, it's not hard to show that the norm of the state vector is actually preserved. So it remains constant. So this is very similar to a unitary time evolution, except that now dynamics is non-linear. So it preserves the norm, but it does not necessarily preserve angles between state vectors. And let me show a concrete example of a quadratic system which is sparse and divergence-free. And this is called Orszag-McLaughlin system. It's a toy model of turbulence. So here we have n variables arranged at sides of a one-dimensional lattice with periodic boundary conditions. And drift functions are composed of interactions between nearest neighbor and next to nearest neighbor variables. So this is a very simple system, but as you can see, it can exhibit very complex dynamics. Another example is a system of coupled nonlinear oscillators. And here we think of an oscillator as kind of a pendulum, and its state can be fully described by displacement angle theta. And so each oscillator has some frequency omega, and some pairs of oscillators can be coupled to each other. So this is a nonlinear system, but obviously it's not quadratic, and it has a second-order time derivative. But we can map it to a first-order quadratic system by a simple change of variables. So here I show how it works for a single oscillator. We introduce a new variable for sine, cosine theta, and for time derivative of theta. And we obtain a quadratic ODE. And it happens to be divergence-free, so it preserves the norm. And it is sparse, assuming that each oscillator is coupled to only a few other oscillators. So this coupling matrix is sparse. And the last example is the Navier-Stokes equation that describes incompressible fluid flow in two special dimensions. So here this V is a velocity field and describing the fluid, and time derivative of V has a quadratic advection term. It has a linear viscosity term and a pressure gradient. And the second equation demands that a fluid is incompressible. And this is a very important system that shows up in many areas in science, engineering, and so on. But unfortunately, this system is not divergence-free according to the definition that I showed you. It does not preserve the norm. but it has a property that a suitable norm of the velocity field does not grow with time, as shown here. And basically, this is due to dissipation of energy. And in the paper, we describe a more general definition of divergence-free systems that includes dissipation. And Navier-Stokes equation is divergence-free according to this more general definition that I don't want to discuss now. So one caveat is that Navier-Stokes is a differential equation, partial differential equation. So it means that we need infinitely many variables to describe the velocity field. But in practice, we always expand velocity field in some basis and truncate the expansion at some finite order. For example, we may use a basis of sine, like Fourier basis composed of sine and cosine waves, and we impose a cutoff on maximum momentum. So this would give us ODE with some finite number of variables n. So if we use a Fourier basis, this ODE is divergence-free, but unfortunately, it's not sparse. And we can make it sparse by choosing a basis with locally supported functions, like in finite element method. So we can get sparsity, but then we no longer have divergence-free property. So Navier-Stokes only partially fits into our framework. Okay, so now why do we believe that solving sparse divergence-free system is a hard problem? And let's begin with the linear case. When ODE is linear, and linear systems are equivalent, linear divergence-free systems are equivalent to solving a Schrödinger equation for this is skew-symmetric Hamiltonian. So this is a problem that we expect a quantum computer can efficiently solve. And indeed, in the paper, we show that this problem is BQP complete. And just to remind you, BQP stands for bounded error quantum polynomial time. And so this is a complexity class that includes all problems that can be efficiently solved on a quantum computer. And BQP completeness means that a problem is contained in BQP, but it is not contained in any smaller subclass of BQP. So it's among the hardest problems that a quantum computer can solve. And if we move from the linear case to quadratic systems, the problem becomes NP hard. So it's as hard as traveling salesman or satisfiability problem or whatever your favorite NP hard problem. And this was conjectured a long time ago by Abrams and Lloyd and proved rigorously by Childs and Jung. So basically, this leaves no hope for an efficient algorithm, neither classical nor quantum. And one small caveat is that this NP hardness results requires time-dependent coefficients in the ODE, but I don't think this is super important. The reason why this problem is so hard is high sensitivity to initial conditions. It means that a very small change in initial state vector at time 0 can result in drastic changes at some later time moment, like in butterfly effect. And this was demonstrated formally by Childs and Jung for a single qubit Gross-Petaevsky model. So this is just single qubit Schrödinger equation. It has time-dependent linear term and a fixed cubic term. So this dynamics preserves the norm of a state vector, but it does not preserve angles. And moreover, we can it's possible to optimize this time-dependent linear term such that angles between state vectors are amplified exponentially. So say we start with a pair of input states separated by angle theta. Then we evolve for time proportional to log 1 over theta. And we get a pair of output states which are almost orthogonal. So we can reliably distinguish them. So Childs and Jung showed that this dynamics can be combined with standard Hadamard test to exponentially accelerate Grover search and efficiently solve NP-hard problems, which is, of course, we believe is impossible. As it written here, this equation is cubic, but you can make it quadratic by looking at time evolution of the density matrix instead of state vector. So then this becomes a quadratic divergence-free ODE. And so this demonstrates that this can be an NP-hard problem. Okay, so obviously we have to do something to sort of mitigate this butterfly effect if we hope to obtain an efficient algorithm. And our solution is to add noise to initial conditions. So we pick some noise rate P, and for each variable in the initial state vector, we add Gaussian noise with zero mean and variance P. So instead of ideal initial condition X, we have X plus delta. Delta is Gaussian noise. And if you think of initial condition as input data for the problem, then noise means that we have uncertainty in the input data, which is not it's not totally crazy assumption. So unfortunately, the runtime of our algorithm scales very badly when noise rate goes to 0. So for practical purposes, this noise rate has to remain constant, say like 10%, maybe 5%. But it's a fixed parameter. Okay, so now I'm ready to define the noisy problem, which is supposed to be hard classically and easy quantumly. So input of the problem is evolution time t, desired initial condition x, and a scalar observable function. So at time 0, we initialize the system by x, we add Gaussian noise, and then we follow the trajectory determined by the ODE. And at time t, we measure our observable function and take expected value over the noise. So this gives some function v of tx, and our job is to approximate this function, say this small additive error. Yes, so this is the problem. And this observable function has to be sufficiently simple. And for concreteness, let's assume it is one of examples that I show here. So this corresponds to computing first moments or second moments of state vector. So for technical reasons, we have to make the problem a bit more complicated. So we are going to modify the equation of motion by adding dissipation and Wiener noise. And this is controlled by a single parameter lambda, the dissipation rate. So the dissipation term shrinks the norm of state vector at the rate lambda. And Wiener noise is a vector of independent Brownian motions with a diffusion constant simply related to P and lambda. And for technical reasons, the rate of Wiener noise has to be related to rate of initialization noise. But this is not super important because we can make both dissipation and Wiener noise extremely small, as opposed to noise in the initial conditions, which we cannot reduce too much. And in the paper, we consider slightly more general setup when this lambda is a vector of dissipation rates. So each variable can dissipate at its own rate. And this allows us to describe systems like Navier-Stokes equations. Okay, and now I'm ready to state our results. So first we can show that for any constant noise rate, there exists an efficient quantum algorithm that solves noisy, sparse, divergence-free quadratic ODEs. So it solves the problem that I defined a couple of slides ago. And the runtime, so this table shows the runtime as a function of various parameters. Most importantly, it scales polylogarithmically with number of variables. It scales polynomially with the evolution time. And this is basically the best we can hope for. The runtime scales inverse polynomially with approximation error, dissipation rate. But unfortunately, it scales exponentially with the norm of the initial condition and inverse noise rate. So our algorithm is practical only if this quantity in the exponent is a constant, preferably a small constant. Now you can ask, but maybe there is a classical algorithm that solves the same problem with a comparable or better runtime. And we have a strong evidence that this is not the case because our problem is BQP hard, or in fact, it's BQP complete. So this BQP hardness persists even if the noise rate is some constant, like 10%, and initial condition is a unit vector, and the system is linear. And basically, BQP hardness is baked into the definition of our problem because noise has zero mean, and in the linear case, it just disappears. So noise doesn't matter in the linear case. So theorem 2 follows almost directly from definitions, and our main contribution is theorem 1, an efficient quantum algorithm. So in the rest of the talk, I want to give you some high-level ideas how this algorithm works. Are there any questions about the result? Okay. So our algorithm follows a standard blueprint proposed in this seminal paper by Liu and others. So here we start with nonlinear classical dynamics in some n-dimensional space. And the first step is linearization. So it gives an equivalent linear dynamics in infinite dimensional space. And usually this linear dynamics describes time evolution of some quantum system. And the most tricky step is Hilbert space truncation. So we have to project this linear dynamics onto some finite dimensional subspace without disturbing it too much. Yes, and the final step is we simulate the projected linear dynamics on a quantum computer. And there are several variants how to implement these steps. But as far as we can tell, all of them have a limitation. So this Hilbert space truncation can be justified only if nonlinearity is sufficiently big. And this might be unavoidable because of NP hardness result that I mentioned. And we get around this limitation by adding noise to the system. So let me begin with linearization step. There are two very popular linearization methods due to Karleman and Kolmogorov. Accidentally, they were discovered around the same time. So Karleman's method is a good choice for solving noise-free systems. And this is why it was used by almost all previous quantum algorithms for solving nonlinear ODEs. And Kolmogorov's method makes more sense for solving stochastic or noisy ODEs. And this is why in our paper we use Kolmogorov's method. So let me begin with Karleman's linearization. And here the main idea is to introduce a bunch of new variables that encode products of original variables, x1, x2, and so on. For example, we could introduce a new variable encoding x1 squared, another variable encoding x1, x2, and so on. In general, we create a new variable for each monomial, like shown here. These monomials are labeled by multi-indices m. It tells us which power of each variable we create. And now any quadratic or even any polynomial function becomes linear because a product of two monomials is always another monomial. So this is the linearization step. So if we start with a nonlinear ODE with n variables, we can compute time derivative of any monomial. We use the chain rule for the derivative, and we end up with a linear combination of these monomials. So we have linearized the system, but the price we pay is that we have infinite number of variables. So it's not immediately clear if this is useful. So what people do in practice is we can impose some cutoff k on the maximum degree of these monomials, and then we project the linearized system onto monomials of degree at most k and solve the projected system. but yeah, so the main limitation is that there is no rigorous bounds on the projection error unless nonlinearity is small compared with dissipation. So this is a huge limitation. So now let me discuss Kolmogorov's linearization. So this is what we use in our quantum algorithm. So we start with a stochastic ODE. It includes dissipation and Wiener noise. So f of x is some nonlinear drift function. We pick some observable function that we want to measure. And then we so suppose at time 0 we start with initial condition. We initialize state vector by x. Then we evolve for time t, and then we measure expected value of observable function, and expected value is over Wiener noise. So we get some function u of t and x. So it describes time evolution of our observable. And this function happens to solve the Kolmogorov equation that I show here. So it's partial differential equation, it's linear, and k is differential operator. It has two terms. The first term describes how observable propagates along trajectories of noise-free ODE. And the second term, highlighted in green, describes diffusive propagation due to Wiener noise. And then, similar to Karl-Lemann's method, we introduce a bunch of new variables, but instead of looking at monomials, we create a new variable for every Hermite polynomials in the original variables. So this multi-index M tells us what is degree of the polynomial with respect to x1, x2, and so on. And there are certain normalization factors, but they are not too important. So these Hermite polynomials happen to diagonalize dissipation plus noise part of Kolmogorov equation. So in general, we can expand a solution of the Kolmogorov equation in the basis of Hermite polynomials, and we get some time-dependent vector of coefficients. And basically, our quantum algorithm tries to keep track of time evolution of this vector of coefficients. So we will create a quantum state, psi of t, such that amplitudes of this state coincide with coefficients in this expansion. And there will be a readout step that extracts the value of this observable from the state psi of t. So the noise here, I don't consider noise in the initial conditions, but it will only be important at this final readout step, and I will clarify this a bit later. So what we are going to do is to map Kolmogorov equation or embed it into the Hilbert space of quantum harmonic oscillators. So let me remind you some basic terminology. Here we consider just a single harmonic oscillator. And you can think of it as kind of a box that can be either empty or occupied by some number of particles, like 0, 1, 2, and so on. And the operator algebra can be described by creation annihilation operators that add or remove one particle. Operator A dagger A counts the number of particles in the oscillator. We have this standard bosonic commutation rules. And basically this oscillator can encode a single real variable, x, such that x and derivative over x are linear combinations of these creation annihilation operators. So what we are going to do is we express Kolmogorov equation in terms of creation annihilation operators from previous slide. And this gives an equivalent Kolmogorov equation describing dynamics of quantum harmonic oscillators. So this is our Hilbert space. Each oscillator encodes one of variables in the original ODE. And solution of the Kolmogorov equation is a state vector psi of t that lives in this Hilbert space. This vector has a finite norm, but the norm is not necessarily 1. And time evolution is controlled by a quantum version of Kolmogorov operator. And we call it Kolmogorian because it plays the same role as Hamiltonian. But this is not an official name. So this Kolmogorian has 3 terms, A, B, and C. A is proportional to the particle number operators. And this is a good term because it penalizes states with a large number of particles. And the number of particles is roughly analogous to degree of monomials in the Karl-Lemans method that I described earlier. And operators B and C are simply related to linear and quadratic part of original ODE. Let me just mention that B and C are anti-Hermitian. This means that B plus C generates a unitary time evolution. But C is cubic in creation annihilation operators, and it does not preserve the particle number. So at time equals 0, we initialize the system in a state that encodes our observable function. And here I assume for simplicity that observable is just a single variable, x1. Then our initial state is just a Fock basis vector with a single particle in oscillator 1. Then we evolve for some time t. We grab our final state, psi of t, and compute inner product with certain readout state that encodes initial condition of the classical system. And this readout state happens to be a product of coherent states. And we can show that this inner product is indeed a solution of our noisy problem. So it gives us expected value of observable function at time t. So we just need to approximate this thing. So So we have the usual setup of quantum simulation, initialization in a simple basis state, time evolution, and readout step. So what is the challenge here? Well, the challenge is that we have to simulate a system of n quantum harmonic oscillators, and we want the runtime to be only logarithmic in n, or maybe polylogarithmic. And we have a system with strong interactions that do not preserve the particle number. So this problem may look completely hopeless, but we managed to solve it. And I want to give you some flavor of how of what is our solution. And for simplicity, let me assume that our ODE is purely quadratic. So then Kolmogorov has only two terms, A and C. And basically, the crux of the proof is to derive upper bounds on the moments of the particle number operator. So psi of t is solution of a Kolmogorov equation, and A is proportional to particle number operator. And for simplicity, let's look at the first moment. So we can use Kolmogorov equation to compute time derivative of the first moment, and we get two terms. The first term is good because it penalizes a large number of particles. And the second term is bad because it can potentially create new particles. So which term wins? And it turns out that for quadratic nonlinearity, the good term always wins. So and this is based on this lemma. It gives operator upper bound on the commutator between A and C in terms of A squared and A. So these operators on the left and on the right are Hermitian. So we are saying that right-hand side minus left-hand side is positive semi-definite operator. And this constant coefficient kappa depends only on sparsity of the ODE, strength of the drift functions, and dissipation rate. And we have similar bounds for commutator between powers of A and C. And we can use these lemmas to prove upper bounds on moments of the particle number operator. And basically, it tells us that the solution psi of t is mostly supported on subspace with a small number of particles. And okay, so the next step is what we call regularization. So we are going to pick some cutoff on the maximum number of particles or maximum energy. And for each cutoff m, we define this regularized Kolmogorov K sub m. And it acts on the full Hilbert space, but interactions are only turned on if the number of particles is at most m. Yes, as I say here. And then we are interested in what happens if this energy cutoff m goes to infinity. So for every value of m, we can solve this regularized Kolmogorov equation and obtain some solution psi m of t. And we can show that this sequence of states psi m of t is convergent, and the convergence rate is roughly 1 over square root of m. So, so this is a good news. So this sequence converges somewhere, but we don't know yet if it converges to the right thing or solution of the exact solution of Kolmogorov equation. But yes, but in fact, we can prove a slightly stronger version of convergence when we measure, we use slightly more stringent distance between states. So when we measure the distance, we insert arbitrary any constant power of particle number operator inside the norm. And in the mathematical literature, this is known as convergence in Gauss-Sobolev spaces. And using this stronger form of convergence, we get exactly what we need. So we can show that solutions of the regularized Kolmogorov equation has a limiting state. The limiting state is a differentiable function of time. And this limiting state solves the original Kolmogorov equation. And we have upper bound on how well we approximate exact solution for any energy cutoff m. Okay, and now the last step is we project Kolmogorov equation on the subspace with at most m particles. We can express this subspace using roughly m times log n qubits. And projected Kolmogorian happens to be a sparse matrix. So the sparsity and the norm scale polynomially with m. And we have upper bound on the projection error. So now we can simulate this projected Kolmogorov equation using standard quantum algorithms for sparse Hamiltonian simulation. And the bottleneck is readout step. So we have to estimate inner product between psi of t, solution of the Kolmogorov equation, and readout state that encodes the initial condition. And this readout state happens to have very large norm, as shown here. And this large norm amplifies errors in Hilbert space truncation and in the sparse Hamiltonian simulation. So unfortunately, it means that the runtime and number of qubits of our quantum algorithm scales polynomially with the norm of the readout state, and it scales exponentially with 1 over p. Yeah, so just to conclude, our quantum algorithm is efficient if ODE is quadratic, sparse, divergence-free. We have to add noise to the initial condition, and the noise rate cannot be too small. So yeah, maybe let me skip a couple of technical slides. Yes, so and we did numerical experiments just to check that our theory is reasonable. And here we looked at this Orszag-McLaughlin system with very small number of variables, n equals 4. This is our observable function. And we compare, well, we approximate this observable with two different algorithms. One is just a brute force Monte Carlo simulation. So we pick a random realization of Widen noise, integrate the system, and we average over many Monte Carlo samples. And the second method is our quantum algorithm. So we simulate Kolmogorov equation, but of course here we use classical computer to simulate it, not a quantum one. And as you can see, solutions obtained by Monte Carlo and by Kolmogorov equation get very close to each other as we increase the energy cutoff. There is still some discrepancy in this region, but my theory is just because we don't have enough Monte Carlo samples. So what I find interesting about this example is that classical simulation of our quantum algorithm is many orders of magnitude faster than brute force Monte Carlo simulation. And this is because Kolmogorov equation gives you expected value of the observable in a single shot. But for Monte Carlo method, you have to generate many thousands of shots to suppress variance. Oh, yes. I am not aware of much better methods. I mean, people certainly used Kolmogorov equation before our work to solve stochastic ODEs. But yeah, if you can suggest a better method, I would be interested. Yes, and the same plot for approximation error. And yeah, so this is my last slide. What have we learned? So I described a large class of quadratic differential equations that preserve the norm of a state vector. And I tried to convince you that adding noise to the equation may have profound implications for computational complexity. So the noise-free problem is NP-hard, but when we add noise, we can solve it efficiently on a quantum computer. And the present version of our algorithm is not very practical because we have to inject quite a lot of noise into the system. But we hope that future work may address this drawback. And so what about practical relevance? Our original motivation was to solve Navier-Stokes equation that I mentioned. But as I said, we need some new ideas to combine sparsity and divergence-free property. So at the moment, we cannot get both. So it's an open problem. And I think that's all I had to say. Thanks a lot for attention.
Thank you very much. Are there some questions? Okay, let me start. So you're trying to use stochasticity to help with standard problems, but there are other issues that are inherently stochastic. So problems like the growth of a surface, KPZ equations, and can one think that this could be of relevance to such problems?
Yes, I hope so. So if your system inherently has some noise and we don't have to edit by hands, then certainly we can apply our quantum algorithm. The main limitation is that we need quite a lot of noise to make algorithm practical.
Another question, I'm counting on you to come up with, so yeah, well, I'll ask mine. Some nonlinear equations are integrable, say the Boussinesq equation or things like that. Maybe they don't fit with your divergence-free situation, but I'm just wondering, and if they could be used as a test bed for some of your studies. We would see solitons emerge, for instance, out of the solutions.
Yes, that's a good suggestion. So we don't expect these exactly solvable models to be NP hard, probably. So it's a good thing.
Yeah.
Of course, once we add noise, say Wiener noise, then we probably lose exact solvability. But maybe for exactly solvable models, we don't even have to add noise. Maybe we can try to to come up with quantum algorithm for noise-free problem. This will be even more interesting.
Thank you. Okay. Behind, yes.
Actually, the initial noise distribution is correlated to the Wiener process in the model. Is this a critical criteria to use, or I mean, how important is this correlation is?
You mean why we choose noise rate for Wiener noise and initial condition noise related to each other?
That's right.
I don't think this is critical. We can certainly make a noise rate for initial condition larger if you want, just by adding extra noise. But I don't think we can reduce it a lot. Yeah, so unfortunately, I don't have non-technical explanation why these two noise rates are related to each other. It comes from properties of Hermite polynomials that we use, basically. So if you don't put enough noise in the initial condition, what can happen is that this redoubt state has infinite norm. So even if you can efficiently solve Kolmogorov equation, the solution does not tell you much, because you have to compute inner product with the redoubt state, and redoubt state has infinite norm. So it's not even a state mathematically.
So my question is, how does the runtime scale with the complexity of the observable you're computing? Because you showed some very simple ones, but say I'm more sadistic and want to consider a more involved function.
Yeah.
Is there you understand the scaling? Hardness?
Yeah, so we can certainly handle more general observables. The only constraint we have is when you expand your observable in the Hermite basis, the vector of coefficients, we must be able to prepare quantum state describing the vector of coefficients. So it's like the data loading problem that we usually have in quantum algorithms. And when this observable is just single variable or say x1, x2, then this data loading is very simple. But I would imagine that it can be solved for more general functions. But we have not looked into this in the paper.
Thank you.
Hi, thanks for the talk. I'm curious about the workflow for designing the algorithm. So I see that in the end, the quantum advantage is ultimately coming from the ability to do sparse Hamiltonian simulation. So I'm curious about what you think about quantum algorithm design more generally. Do you think that the most promising thing is to look for problems that we have exist like classically or quantumly, and see like whichever problem, try and see like, can this problem be transformed into a sparse Hamiltonian simulation problem? Do you think that's the most promising strategy in general, or do you think there are other ways to, there's something else that we can also do with quantum, build quantum algorithms based on different principles as well?
Yes, so I think the most promising application area for quantum algorithms is certainly simulating quantum physics. But I mean, we can apply fast Hamiltonian simulation techniques to completely classical problems which have nothing to do with quantum physics. For example, in machine learning and topological data analysis, we apply well, basically the goal is to compute Betti numbers for certain simplicial complexes, and the way quantum algorithm works, it applies Hamiltonian simulation to a combinatorial Laplacian describing this complex. So I think what you said certainly might make sense to look for classical problem that can be solved with Hamiltonian simulation methods. And in this talk, I guess I gave another example.
Okay, thanks.
In the back.
Hello, thank you for your presentation. So basically, in your scheme, you linearize your differential equation in order to implement it on a quantum computer. Is it possible to still implement like a nonlinear evolution on a quantum computer? I know that like quantum computing is, well, unitary and non-linear only, but is it still possible to do it, like to do block encoding or something like that?
Yes, so there was very old paper from Tobias Osborne that I think does that. So we give quantum algorithm for solving quadratic ODE, and it's not based on any linearization method, but it has to use post-selective measurements in order to simulate non-linearity. And because of this post-selection, the runtime grows exponentially with the evolution time. So it's logarithmic in the number of variables, but it's exponential in evolution time. So I'm not sure how practical is it.
So the nonlinearity is implemented through measurement, right?
Yes.
But it's not possible to do it like directly nonlinear implementation on a quantum computer.
I don't think so, because quantum mechanics is linear. So at some point you have to linearize things.
Okay. Thank you.
Okay. All right. Well, we thank Sergey again, and we'll see you next time.
Okay, thank you very much.